Over the last year, there's been a lot of excitement around building AI agents, especially as we move into 2026. This has made it seem like agents are something entirely new. In fact, agent-based systems have existed for decades. What's changed is not the idea of agents, but how broadly and practically they can be applied today, largely because of powerful large language models. To understand AI agents today, we need to look at how decision-making has evolved. Early agents from the 1950s through the 1980s reasoned by searching through defined state spaces. They were effective but brittle as adapting required rewriting rules by hand. In the 1990s, the focus shifted to agent architectures. Models like reactive agents, planners, and BDI systems gained autonomy through internal state and explicitly represented beliefs, goals, and intentions through dynamic action. By the 2000s and 2010s, machine learning shifted the focus to data-driven optimization. Instead of hard-coding every behavior, we used reinforcement learning to let agents discover their own policies and value functions through trial and error. Deep learning allowed agents to process images, speech, and sensory data at scale, but reasoning was still flawed. Today, the integration of large language models has fundamentally changed the stack. We can now build agents that reason, plan, and utilize tools across a vast range of tasks. The core idea hasn't changed, but the capabilities have. This is why 2025 felt like a breakout year. Large language models reduce how much logic needs to be hard-coded and make it easier to build agents that handle unstructured input, complex goals, and multi-step decision-making. Agents aren't new, they just finally stopped sucking. You can already see this in today's tools. Cursor AI behaves like a coding agent. It understands context across files, proposes changes, and iterates as you refine your intent. Multimodal web agents can interpret screenshots of the web page, interact with interfaces, and adapt when layouts change. They can see the web as humans do. These systems don't stop after one response. They operate in loops. Under the hood, every agent shares a common, continuous control loop structure that bridges the gap between logic and action. To understand how this loop functions, think of the difference between a static GPS and a self-driving car. A standard AI model is like a GPS, a passive tool that computes a route when prompted but has no goals of its own. An AI agent is the self-driving car, a system that takes initiative and perceives its surroundings in order to reach a destination. To move beyond basic prompting, we have to architect for 4 distinct stages. First, the agent observes. Continuing the self-driving car analogy, the agent uses environmental sensing. It transforms raw data into meaningful signals it can process. Next is reasoning, which acts as the car's navigation. Powered by an LLM, it doesn't just follow a fixed scheme, it decomposes high-level goals into subtasks and generates a reasoning chain to decide the next move. Then, the agent acts using the hands of the system. Whether it's calling an API, querying a database, or executing code, the agent interacts with its environment to produce real-world results, with memory keeping an internal state to make sure it doesn't get lost. Finally, and most crucially, the agent adapts. Think of it as if a road is closed, the car reroutes. The agent analyzes its own decisions and outcomes to correct its course in the next iteration. Architectural patterns like react, reflect, and adapt are different ways we can organize this loop to turn a basic script into a production-ready system. A clear example of this architecture in practice is Eureka, a reward design agent from reinforcement learning research. Here, the agent isn't just acting in an environment, it's adapting to the objective itself. Given an environment definition and a task description, a coding language model generates an initial reward function. The system then runs a simulation, observes performance metrics, reflects on what's working and what isn't, and programmatically revises the reward code. In this case study, we focus on Brax half-cheetah environment. While NVIDIA demonstrates this at a massive scale, we can explore the same fundamental principles on a smaller scale. For our demo, we use the half-cheetah benchmark in the Brax physics engine, a simple lightweight simulation optimized to run on free resources like Google Colab. Let's take a look at our initial state. It's obviously not looking good for this newborn cheetah. The system runs a simulation, observes the cheetah's speed and other metrics, identifies what's not working, and revises the reward. You can see it get better in this next run as the agent adapts to the objective. In this final iteration, you can see the model's performance is the best so far as it adapts to the objective of making the cheetah run forward as quickly as possible. This is a relatively low-code way of visually understanding how models self-improve, but the same underlying principle is at work in everything from self-driving cars to ChatGPT. If you want to design systems like this, the key is going beyond prompting and understanding architecture. Educative's courses cover how to build AI agents using modern frameworks, how multi-agent systems are designed, and how real case studies inform good agent architecture. You can find links to relevant courses in the description. Thanks for watching.